everybody. In fact, the aim of this talk is to show you how we can combine the high sensitivity and also simplicity of the laser optical feedback imaging with the high resolution of the synthetic aperture imaging to finally obtain a plenoptic microscope, which allows the imaging through heterogeneous and turbid medium. And this work is carried out in the laboratory for interdisciplinary physics of the Université of Grenoble in France. So the outline of my talk are, firstly, I would like to explain you the principle of the LOFI method, which is based on frequency-shifted optical feedback. Secondly, I would like to briefly do some recalls about the synthetic aperture method, about the synthetic aperture imaging, mainly used in the radar domain, and how it can be extended to the optical domain. Thirdly, I would like to explain you how it is possible to build a plenoptic microscope by using the synthetic aperture LOFI signal. So to start, a LOFI experiment, what is it? Firstly, LOFI means laser optical feedback imaging, and the LOFI method is an interferometric method which uses the high sensitivity of laser to frequency shift optical feedback. In fact, here we can see a typical Here we can see a typical experimental setup for a LOFI experiment. And as we can see, the LOFI microscope is very similar to confocal microscope. Indeed, there is a laser source, there is an object under investigation, there is a frequency shifter, and there also a detector. But the main difference between the LOFI microscope and the confocal microscopes come from the beam splitter orientation here. Indeed, in the LOFI method, before detection, the feedback field is frequency shifted and reinjected inside the laser cavity to generate a beating. And after, a small part of the laser output power modulation is detected by using the beam splitter and a conventional photodiode. So the LOFI microscope is a kind of active confocal microscope where the laser is simultaneously the source and also the detector and also an amplifier. At resonance, when the frequency shift is equal to the relaxation frequency of the laser, the output power modulation of the laser is given by this equation, where we can see that the LOFI gain is given by this ratio. This is the damping rate ratio between the damping rate of the laser cavity and the damping rate of the upper level of the laser transition. With our laser, which is a microchip laser, a laser with a very small cavity, this damping rate ratio is of the order of 1 million. This means that the feedback reflectivity as low as 10 to minus 12 leads to an output power modulation of 100%, which is very easy to detect. And the high sensitivity of the LOFI method comes from this resonant amplification, which allow very interesting application in a very simple manner. So for LOFI experiment, principally we need of a laser, a special laser, a class B laser, and we also need a frequency shifter. To obtain a good LOFI signal, we need to use a class B laser. A class B laser, that is to say, a laser which exhibits relaxation oscillation, as we can see on this graph showing the time evolution of our microchip laser during its starting up. As we can see on the radio frequency power spectrum, which is shown here, the relaxation frequency of our microchip laser is in the megahertz range. Secondly, in the LOFI microscope, to obtain a beating between the feedback field and the intracavity electric field, we need to use a frequency shifter. And to obtain a resonant amplification of the beating, the frequency shift also need to be in the megahertz range. And experimentally, our frequency shifter is composed, in fact, of two successive acousto-optic modulators working respectively at 80 MHz and 81 MHz to finally obtain by difference a frequency shift in the megahertz range. So the high sensitivity of the LOFI method comes from this resonant amplification when the frequency shift here is equal to the relaxation frequency of the laser. This picture shows the first application with the LOFI method. In this experiment, we have this is imaging through turbine medium. This is imaging through fog, in fact, in the aim of assistance for car driving. And this experiment, we have imaged a road sign here, located 40 meters away from the laser through a calibrated turbine medium composed of water and milk, in fact, in a tank. And for a better understanding of the LOFI signal, the size of the tank is very small, and the tank is only located on the left side of the road sign. And the experiment has been made for different milk concentration, and at the end, the diffusion is so important that we are unable to see through the tank. But even through this very dense fog, the LOFI signal is able to read the number 1, which is written on the left side of the roadside. So the LOFI setup seems to be well adapted for imaging through dense turbid medium. On this picture, we can also observe that on the right side of the road sign, the LOFI signal is unable to read the letter M, which is written here on the right side of the road sign. This is due to the fact that in the air, the amount of optical feedback is too big, and the LOFI signal is completely saturated. The laser is completely saturated. So the LOFI setup is very interesting for imaging through dense turbid medium due to its high sensitivity. The second application, which is shown here, is phase measurement experiment. And the target under investigation is a concrete structure which was cracked with a shock. And as we can see, the crack is important on the back side of the concrete structure and non-emerging on the front side of the concrete structure. Therefore, therefore it is unable to see the crack when looking on the front side of the concrete structure. And experimentally, the acoustic stimulation of the concrete is made with a loudspeaker at low frequency of 150 Hz. And the LOFI phase image, which is obtained here, is simply a measurement of the amplitude of the vibration of the concrete structure on the front side. And as we can see, the LOFI signal is able to detect a difference in the amplitude of vibration on both sides of the crack. So again, due to its high sensitivity, the LOFI method is able to detect a non-emerging crack in the concrete structure. This slide shows the performances of the LOFI method for amplitude and phase measurement. For amplitude measurement, this slide shows that when the LOFI signal is not saturated, here the LOFI signal is saturated, and when the LOFI signal is not saturated, the LOFI signal is shot noise limited. Therefore, we are able to detect with the LOFI setup feedback reflectivity as low as 10 to minus 13 when we work with a laser with an output power of 10 milliwatts and with a detection bandwidth of approximately 1 kilohertz. So the LOFI setup is very sensitive. The second graph here shows that with the LOFI setup for the phase measurement, we are able to detect displacement or vibration amplitude of the order of 1 angstrom, and this even if the feedback reflectivity is very low. So again, the high sensitivity of the LOFI method comes from the resonance amplification of the beating inside the laser cavity. So to summarize what is LOFI, so firstly, LOFI is an interferometric setup which allows to register the amplitude and the phase of the feedback electric field. And one of the main advantages of the LOFI method is that the setup is auto-aligned due to the fact that the laser is the source and also the detector. So no complex alignment are required. Thirdly, the LOFI signal is shot noise limited. This is due to the resonant amplification of the laser quantum noise. And due to this resonant amplification, the quantum noise is above the shot noise limit. And the main drawback of the LOFI imaging comes from its slowness, in fact, due to the fact that the images are obtained point by point, line after line. And to obtain an image of 100 by 100 pixels roughly takes approximately one second due to the lifetime of the upper level of the laser transition. So the main drawback of the LOFI imaging is its slowness, in fact. But the sensitivity is very high. And now the second part of this talk, I would like to explain you the synthetic aperture LOFI. Firstly, I would like to explain you the principle of the synthetic aperture process, the principle of the synthetic aperture method, which is principally used in the radar domain. And when looking at the punctual target, the synthetic aperture radar can be simply explained in the following manner. So when looking at the punctual target, we can define the radar initial position as the position where the punctual target enters into the diffraction spot and then becomes to be observed. The diffraction spot is characterized by its diffraction angle. And due to the radar scanning, due to the radar displacement, the target goes through the diffraction spot. And we can define the radar final position as the position when the punctual target goes outside the diffraction spot. And between the initial position and the final position, we can, of course, define the numerical aperture of our setup. The numerical aperture corresponds to the angle where the punctual target is observed is seen by the radar. And this picture clearly shows that the numerical aperture is simply given by the diffraction angle, in fact. And now, if we define the the resolution of our setup by the ratio between the wavelength and the numerical aperture, one simply obtains that the resolution is given in the synthetic aperture method by this parameter, which is simply the size of the radar source. And this, whatever the distance between the punctual target and the radar displacement plane. So the resolution, it is important, is independent of the distance between the radar and the punctual target. Experimentally, in fact, how does it work? In fact, the synthetic aperture process is simply a correlation calculation between the reflected signal and an adapted filter. And when looking at the punctual target, the upper graph here shows the time evolution of the reflected signal during the scanning of the radar. And as we can see, due to the Doppler effect, the reflected signal is a kind of chirp pulse. And for a single punctual target, the adapted filter is simply the time reversal of the signal, as we can see here. And finally, the synthetic aperture signal, which is simply the modulus of the correlation calculation between this signal and this one, is shown here. And as we can see here, if we compare now the upper graph with the lower graph, we can see that the synthetic aperture process allows to compress the time response of the reflected signal and therefore allows to increase the resolution. And now for a double punctual target composed of two individual reflectors, the time evolution of the reflected signal is much more complicated. But by using the same adapted filter, we finally obtain the synthetic aperture signal, which is shown here, where the two reflectors are now clearly resolved. So now I would like to explain how it is possible to extract from the LOFI setup a synthetic aperture image. To begin, I recall you that in the LOFI microscope, again shown here, the resolution of the image is simply given by the size of the focal spot, which is focused on the object, and that the image is obtained by a scanning of the laser beam on the object. But now, what's happening if we increase the measurement distance, if we move away the object here from the focal plane of the lens? And by doing this, in fact, we have exactly in the same experimental condition that those previously mentioned when we speak about the synthetic aperture radar. But now the radar source is just replaced by the focal spot of the laser beam, which is here, in fact. So, by using the scanning of the laser beam on the object and by using the synthetic aperture process, we hope to be able to recover the initial optical resolution of our microscope, and this even if the object is not in the focal plane of the objective, and this whatever the distance between the object and the focal spot of the laser beam. So to test the possibility to obtain a synthetic aperture image with the LOFI setup, the target under investigation is composed of silica beads like this with a diameter of 30 micrometers, and the silica beads are located behind the P-shaped hole with a width and an height of the order of 1 millimeters. So here we make a comparison between conventional LOFI image obtained here and a synthetic aperture image which is obtained with this setup. So the first image which is shown here is a conventional obtained LOFI image which is obtained with a lens having a high numerical aperture, and as a result, with high numerical aperture, the silica beads which are located behind the P-shaped hole is resolved. The second image, which is shown here, is an image of the same object, but obtained with a lens having a lower numerical aperture at a longer observation distance. And as a result, now, due to the lower numerical aperture, the silica beads can't be resolved, and only the P-shaped hole is distinguishable. And finally, to obtain a synthetic aperture image, that is to say an image with a high resolution of a far object, we have used the lens having the high numerical aperture, and we have imaged the object with a defocused laser beam. So by doing this, we have obtained this blurred image, but after we do the 2D synthetic aperture process, and the 2D synthetic aperture process allows to recover the initial optical resolution of our microscope, and this even if the object is at a is not in the focal plane of the objective. Okay, so here we have the confirmation that with our LOFI setup, which is an optical setup, we are able to obtain a 2D synthetic aperture image in the optical domain. So it works, but there is a drawback with the synthetic aperture method. This drawback comes from the small numbers of photons which are collected to form the synthetic aperture image. Indeed, the number of photons, this drawback is characterized by the fact that the number of photons decreases proportionally to the square of the distance between the focal spot, and the target. And this drawback is due to the confocal filtering of the optical reinjection. And due to this drawback, the LOFI synthetic aperture setup is very sensitive to parasitic optical feedbacks coming back from the different optical elements of the target. And therefore, to increase the LOFI sensitivity, we need to reduce the effect of the parasitic optical feedback. So to reduce the effect of parasitic optical feedback, we use the setup which is shown here. Indeed, so in order to reduce the unwanted reflection coming back from the different optical elements of the target, we have used, in fact, acoustic photon tagging, which with acoustic photon tagging, we are able to eliminate the parasitic optical feedback coming back from the different optical elements of the target. And by this acoustic photon tagging, by this filtering, we are able to reach the shot noise limit, and therefore we are able to see object at a deeper length inside the turbid medium, for example. So to do this, to reach the shot noise limit, we need to tag the photon just before the target, that is to say, after all the optical elements of the target. For acoustic photon tagging, in fact, we have used the acoustic transducer, which is shown here, and with this transducer, we have focused an acoustic wave on the focal spot of the laser beam. And with the complete experimental setup, which is shown here, we have imaged now a target which is always composed of silica beads, but the silica beads are located now behind the circular hole with a diameter of 1 millimeter. And the target is filled, is placed inside the rectangular glass tank, and the tank is filled with milk and water again. And the milk is a kind of turbine medium, is a kind of scattering medium. And in this experiment, in order to detect only the tagged photon, the signal is demodulated with a locking amplifier, which works at a reference frequency of Fe minus Fa instead of simply Fe without acoustic photon tagging. And experimentally, we have chosen Fe equal to 4.4 MHz without acoustic photon tagging, and with acoustic photon tagging, we have chosen Fe equal to 8.9 MHz, Fa equal to 4.5 MHz, to finally obtain a difference in frequency equal to 4.4 MHz. So in both cases, the total round-trip frequency is equal to 4.4 MHz, In this condition, we have the same LOFI gain between these two kinds of experiments. So the upper graph here, the comparison of the upper graph here with the lower graph here shows an improvement of the image quality with acoustic photon tagging, and the improvement of the image quality is characterized by a reduction of the background, and also is characterized by an improvement of the contrast of the image. In both cases, from the raw image here and here, we are able to obtain a synthetic aperture image where the beads are well refocused, in fact. So with acoustic photon tagging, we are able to increase the quality of the image. We are able to reach the shot noise limit of the LOFI detection, due to the fact that now we don't have any parasitic reflection coming back from the objective, coming back from the frequency shifter, coming back from the scanner in our experiments. So now the third part of this talk about the Plenoptic LOFI microscope. And in fact, the synthetic aperture process, the adapted filtering which is used in the synthetic aperture process, can be simply interpreted as a numerical raw focusing of a blurred acquired image. Indeed, the LOFI setup is an interferometric setup which allows to register point by point, line after line, the amplitude and the wavefront of the feedback electric field, that is to say, the numbers of photons in each propagation direction. And here, we can see a blurred complex image which is acquired when the target is illuminated with a defocused laser beam. And this fact, this image, as we can see in this equation, is simply a blurred complex image of the target. So after the experimental acquisition of this complex wave, one can use, the free space propagator, which is shown here, to numerically propagate back the complex wave in the focal plane of the objective. So we can do this operation, we propagate back, you see here -L, with the free space propagator, and we finally obtain the good image in the focal plane of the objective. The graph, the lower graph here, shows an example of a numerical raw focusing for a target composed of silica beads, always locating behind the P-shaped hole. And in this graph, we can see how the numerical raw focusing occurs when the filter mismatch, given by this equation, decreases to finally achieve the adapted filters. So when the filter is well adapted, we obtain a clearly very resolved image where the beads is clearly resolved and is very well seen behind the P-shaped hole. So in fact, the synthetic aperture image obtained with our LOFI setup is simply a numerically refocused image after the acquisition of the raw complex image, which is shown here. So now this slide shows that numerical refocusing is also possible on the curved surface with our Plenoptic LOFI microscope. Indeed, obtain a 3D pseudo-image, that is to say, an image of a non-flat surface, by the way of a 2D scanning, is an important characteristic properties of a Plenoptic microscope. And in this experiment, in fact, the target under investigation is a flexible tissue with silica beads on its surface, and the tissue is voluntarily curved to obtain a non-flat surface. And the first graph here, the image A, shows the raw defocused image we obtained with the laser beam is defocused on the target. The second image, which is shown here, the image B, is a synthetic aperture image after a numerical refocusing on an intermediate plane given by a distance of L equal to 750 micrometers. On this image, one can see that only a small part of the image is sharp. Only a small part of the beads are sharp due to the fact that only a small part of the beads are well refocused. Finally, the image C shows the best focusing surface, and the image D is the synthetic aperture image on this surface. And on this image, one can see that now all the beads are sharp due to the fact that all the beads are well refocused, and this despite their different initial position along the optical axis of our setup. So with our LOFI Plenoptic microscope, we are able to focus on any surface, and this is an example of a curved surface here. This slide now shows the capabilities of our Plenoptic LOFI microscope for the numerical correction of optical aberration, in fact. And again, here we have image silica beads, and we have image silica beads. And in this experiment, contrary to the paraxial lens usually used, we have used a lens which introduced large optical aberration in our setup. And this lens, which is introduced in our setup, is a paraxial, is a plano-convex spherical lens which is voluntary tilt in the setup to introduce large asymmetrical aberration relatively to the optical axis, and principally astigmatism and coma, in fact. So here, so the target, here the blurred acquired image obtained with the defocused laser beam. From this image, firstly, the defocused is removed, which leads to figure C, where only remains the higher orders aberration. Then astigmatism and coma are removed, leading to figure E. And this figure can be compared with this one, which is an image of another part of the target obtained with the lens without any aberration. And finally, the image DE shows the initial PSF, which illustrates the aberration which are initially present in the objective, and where we show the aberration, we are numerically corrected from this image to this one. Just by the comparison of figure C and figure E show an improvement of the image quality, which shows that it is possible to do numerical correction of optical aberration with our LOFI setup. But the comparison of figure E with figure F also shows that actually our numerical correction is not perfect and need to be improved, in fact. So to summarize this talk, I would like to briefly recall the main specific advantages and disadvantages of the Plenoptic LOFI microscope. So firstly, our Plenoptic LOFI microscope allows to associate the high sensitivity and simplicity of the laser optical feedback imaging with the high resolution of the synthetic aperture imaging. And therefore, our Plenoptic LOFI microscope allows to obtain in-depth image through turbid medium with a very high resolution. And the resolution is independent of the depth inside the medium. Secondly, another advantage of the Plenoptic microscope is the Plenoptic microscope using the LOFI setup is an interferometric setup which allows to register the amplitude and the wavefront of the feedback electric field. And knowing the wavefront, we are able to focus on any surface, and we are able to numerically make a numerical correction of optical aberration. So our Plenoptic microscope is well adapted for imaging through heterogeneous medium. And the main drawback of our Plenoptic LOFI setups come from the photometric sensitivity, the photometric counting. Indeed, the number of photons which are collected to form the synthetic aperture image is very small. This is due to the confocal filtering of the optical reinjection. But this drawback is partially compensated by the high value of the LOFI gain. I remember that the LOFI gain of the order of 1 million, and the LOFI setup is very sensitive. So there is a drawback due to the small number of photons, but there is an advantage due to the high sensitivity of the LOFI setup due to the resonant amplification of the beating inside the laser cavity. And finally, I would like to say that this work is carried out in a team called OPTIMA, Optics and Imaging, in the Laboratory of Interdisciplinary Physics of the University of Grenoble. And the people who are involved in this work are Olivier Jacquin, Olivier Hugon, Hugues, Guillet, Chatellus, and principally 2 PhD students, Arnaud Winsonsky and, of course, Wilfried Glastre. Thank you very much for your attention.